Henriette, are you there? Okay.
Yes, I'm right here.
Oh, there you go. Couldn't see your video. Now I see your video. Okay. All right, you ready?
I think so.
Okay. Let's get started. So we're very happy to have Henriette for her second lecture. Take it away.
All right. Hey, everybody again. So in the first lecture, we studied scalar models, and I talked about locality, that the poles are in exactly the right places where they are. They're simple poles only in 3 amplitudes. And on those simple poles, the amplitudes factorize into lower point amplitudes. We talked a little bit about dimensional analysis, and we talked about symmetries. And in particular, I showed you how imposing constraints on the amplitudes allow you to engineer theories and show their unique properties, such as, for example, that dBi came out of soft theorems. So those were soft limits of a single particle going soft, where the amplitude went to 0. Now, in lecture 3, we're going to talk about the soft limits where amplitudes have soft limits that are divergent. That means sigma is less than 0. And when sigma is less than 0, well, of course, the amplitude blows up. And we've seen one case of that already for scalar amplitudes. That's when you had a cubic interaction. But for scalar amplitudes, that's pretty much it. So in order to get something more interesting, and we'll find something quite interesting, in fact, when we study soft limits that are divergent, we need to study particles with spin. And so for this purpose, I want to introduce to you the 4D spin helicity formalism. So now imagine when you're going on vacation somewhere, and you're going somewhere really awesome. You're going to Hawaii or the Bahamas, and it's an awesome beach, and you're going to have a great time, but you actually have to get there. And to get there, you need to sit for several hours with 2 face masks on in the middle seat on a crowded plane. And you're going to do it because it's important to get there, because you have a really good time when you get there. So this lecture is a little bit like that. It is the plane ride to the really cool place. And so for about 20 minutes or so, that's our plane ride. It might feel like 15 hours, but I'll try to make it light. But I do want to give you the details. The simple approach would be to just throw the formalism at you and say, here's some formalism. It doesn't connect to anything you know, but now we're going to use it. But I want to connect it to what you guys already know from the point of view of standard quantum field theory and Feynman diagrams. All right, so fasten your seatbelts, tuck into your middle seat, and here we go. So we're going to be concerned here with 4D massless particles. There's a parallel for massive particles. It's just technically a little bit more involved. So we'll just stick with massless particles. And that's really what we need for the soft limits anyway. Now, massless particles are characterized by a helicity. And the helicity tells you practically if the spin points in the same direction that the particle is going, or if it points in the opposite direction. So plus and minus helicity for something with spin. Now let's recall some Feynman rules of particles that we know about. Scalars, external rule is 1. Fermions have external wave functions that are typically denoted something like u plus minus and so on. Let me try to get this a little bit of a figure marker. So u plus minus, u bars, and these are for fermions, ingoing and outgoing fermions and antifermions. And we say that fermions are things that have helicity plus and minus 1/2 in 4 dimensions. Then we have vector particles like photons and gluons. They come dressed with polarization vectors as the external Feynman rules. And these have helicities that are plus and minus 1. And we'll also encounter later on gravitinos and gravitons with respectively spin 3/2 and 2. And so they have helicities plus minus 3/2 and plus minus 2. And the polarizations can be made out of the polarizations of the spin 1/2 fermions and the spin 1 vectors, as I've indicated here. So all we need to figure out really is how to deal with spin 1/2 and spin 1. Now for massless particles, we're going to use crossing symmetry. That means that normally you have amplitudes and diagrams with incoming particles and outgoing particles, but we're going to flip all the incoming one to be outgoing. So if you have something with positive helicity coming in and you flip its momentum around, now that means flipping the helicity also. So that means that u flips to v, but with the opposite helicity assignment. And likewise for v bar and u bar, they get related this way. So we just basically need just half the variables. Now we're going to introduce this bracket notation that I've written here. And this is a little pre-written in the beginning, but once we start using this formalism, I'll write in real time. And the notes will be posted too, so you don't have to scribble down everything. So let's go and take one step at a time. So for a fermion coming in, so a fermion going out, we use a U bar. If it has positive velocity, we're going to select a basis of the 4-component Dirac spinners, in which there's only a part in the first 2 entries, and we call that thing a square spinner. On the other hand, if it's a V plus, so it's an antifermion going out, then it's going to be also in the first 2 entries, but we call it a bracket, which is flipped around the other way. Now, those 2 square spinners are related by one having up index and one having down index, and you raise and lower these indices with the 2 index Levi-Civita symbol. And then there's a parallel story when we go to negative helicity. So this was the positive helicity, 1/2. Negative helicity, the U bars with negative helicities have entries only in the 2 second, the 3rd and the 4th entry. We denote those by dotted spinners. So those are the angle spinners P, and likewise for V minus, there's also an angle spinner P. And again, you can raise and lower the index on these things, and that's how they're related through the contraction with the Levi-Civita. Okay, so that's a lot of stuff, but the main thing to remember is square spinners are things with positive helicity, angle spinners are things with negative helicities. So just keep that in mind, and then we won't need all the details, but basically these are the external wave functions that you need for fermions with positive and negative helicity 1/2. So let's understand a few properties of these things. And by the way, feel free, of course, to interrupt with questions at any moment. So spinners satisfy the Dirac equation. And if I go to momentum space, that derivative becomes momentum, and the slash means that it's dotted into into the Dirac matrices, the gamma matrices. And so in momentum space, it's basically P slash and U has to be 0. Now, what is P slash? Here I'm choosing some basis for my gamma matrices in terms of the Pauli spinners, sigma mu and sigma mu bar that you know from your quantum field theory classes. And when I dot in P, this matrix decomposes into a 2x2 block form. And I have a 2x2 matrix P with lower indices and one with upper indices with this type of structure. If you studied supersymmetry, this is sort of this index to index notation that you see come up there all the time. If I wrote out explicitly what this means, it means for the P 2x2 matrix with lower indices that it has these entries that I'm showing you here. And you could then see that if you computed the determinant of that 2x2 matrix, it is exactly the same as P squared, so P contracted with itself. And so the on-shell condition for P, that P is 0, that it's massless and on-shell, is exactly the same condition that says that this matrix, 2x2 matrix, has determinant 0. Okay, so what? So if it has determinant 0, but it's not a vanishing amplitude, sorry, a vanishing 2x2 matrix, it must have rank 1 instead of rank 2. In particular, that means that it has a null vector. What are those null vectors? Those null vectors are exactly the angle and square spinners. How do we see that? Well, we see that by going back up to our Dirac equation and seeing that P slash acting on U has to give 0, but our U's and our V's are given in terms of P angles and P squares. And so they will end up dotting in just the right way that the indices you might anticipate as matrix multiplication, and that gives you 0. So another way we could have introduced the angle and square spinners would have been to say, oh, these are exactly the left and right multiplication null vectors of the 2x2 matrix P. They must exist because that matrix has only rank 1 instead of rank 2. Okay, so far so good. Now, when you learn quantum field theory, you learn to calculate amplitudes, and you also learn to calculate cross sections. And to calculate cross section, you sometimes calculate spin average cross sections. And to do those, then you learn to do these spin sums. And these spin sums, to do them, you have sort of spin completeness relations that says that when you sum over spins, in this case, helicity, so in this case here, I'm summing over U, helicity minus helicity plus for U, U bar, then I get minus P slash. Now let me use this crossing symmetry that related my U minus to a V plus and a U plus to a V minus. And let me then take what I wrote above for the U plus, so for the U bars and the V plus minuses, and plug that in. Sorry, this little typo here, this should have been a plus. There we go. Okay, so this gives me a multiplication of a column with a row. That's a 2 by 2 matrix, and so is the other one. And putting this all together, you can do the multiplications. You get that the following 4 by 4 matrix has to equal the 4 by 4 matrix that is P slash that we wrote down before. So what does this tell us? And that's the upshot of this little calculation here, is that momentum as a 2 by 2 matrix can be written in terms of a product of 2 by 2 vectors. And that is in fact a well-known fact that when you have a 2 by 2 matrix that has determinant 0 and has therefore rank 1, it can be written as a product of two vectors. And somehow this is the place that people often skip to when they introduce these labels. They say determinant of this 2 by 2 matrix is 0, therefore it can be written in terms of two component vectors, or spinors in this case, because they actually spinor transform indices. But now we see where it comes from. It's just the completeness relations from the external wave functions. And it also teaches us one other thing, and that is what this even has to do with amplitudes, namely that these angles and square spinors are the external wave functions of fermions with negative and positive velocities. All right, let me pause there for a second and see if there are questions. All right, we're all sitting in our uncomfortable middle seat on the plane, but we have to go to the nice beach. So let's keep going and feel free to interrupt. So amplitudes are Lorentz invariant quantities. And so that means that they must depend on variables with fully contracted Lorentz indices. So for that reason, it's very useful to define spinor brackets. And spinor brackets are exactly what you get when you take our angle spinors and contract the indices. So you sum explicit sum convention here with the sum over the dotted or undotted indices, and I use some up-down convention that is similar to Wesenberger. Okay, so I and J here refer to momentum Pi and Pj, so that's a little bit of a shorthand notation that we use there. Now, because we raised and lowered the indices here, we raised and lowered them with Levi-Civitas, that means that these products are antisymmetric. And so that antisymmetry translates into the property that the angle and square brackets must be antisymmetric under interchange of the arguments. In particular, that means that if I take an angle bracket P with an angle bracket P itself, that must be 0. So I can only take angle brackets for things that are distinct momenta. Okay, so let's do another little calculation here. We'll multiply together two brackets, an angle and a square with the same labels. And in order to write this, when we write something an angle and square spinor, that must mean that those momenta are on shell. So I'll flip the order of the angle that cost me a minus sign. And then I realize when I look at it that these two guys here, they make up exactly Pi. So that part here is Pi. And these spinors are commuting, so I can rearrange them without any cost of signs. And so I can also pick up my J angle and my J square and put those together into a Pj. And then what we see is that the indices are nicely contracted the way you would do matrix multiplication. So this whole thing is nothing but the trace of the 2 by 2 matrices Pi multiplied with Pj. I know how to deal with traces of momenta from my quantum field theory class. So this actually comes out with all factors right as 2 times Pi dot Pj. And because these guys are on shell, this is nothing but the Mandelstam variable Sij for the particles. So now everything we did for scalars before, all the amplitudes for scalars depended only on Mandelstam variables. So now I can translate everything that we did before into things which has angles and square brackets instead. Why would I do that? Because once I start introducing fermion and vectors, they will come with their own angles and square brackets and get dotted into momenta and each other. Now I have a siren outside, so I'm going to close my window. 1 second. That is the Tuesday 1 o'clock siren in Ann Arbor. Okay. All right. So the upshot of this calculation was that Mandelstams can be written in terms of angle and square brackets. Momenta can be written in terms of angle and square brackets. Let's do an example. So suppose I have some Yukawa coupling, so something with phi vial fermion times vial fermions plus its conjugate. Then the way you might deal with this, now here I mixed things up a little bit, written in the usual notation. You could write this in the standard Dirac spinor notation. But let's just forget completely about the U's and the V's and everything. And just remember the statement that positive helicity is square spinors and negative helicities are angle spinors. Then if I in particular pick this diagram here with positive helicities on the first and second state and negative on the last state, and a scalar propagator in between, that scalar propagator is 1 over P1 plus P2 squared. I'm being casual with i's and minuses to illustrate the ideas. Then you see that this whole diagram will have the 1 over S12 from the propagator, and there's only one Lorentz invariant way of contracting the indices of these spinors. So I get square spinor 1, 2 from the left side and square angle spinor 3, 4 from the right side. And this actually simplifies a little bit because I know that S12 is the same as S34 by momentum conservation at 4 point. S34 is angle 3,4 times square 3,4. I plug that in and you see now that the angle 3,4 will cancel and it leaves the expression as square 1, 2 divided by square 3,4. So this gives you a tiny sense of the type of simplifications that happen when you use spinor helicity formalism. In fact, this would be the entire amplitude with 4 external fermions with these labels. If I flipped one of the signs over here, then there's no way to make a Lorentz invariant contraction, and I can immediately conclude that such an amplitude must vanish.
Sorry, can you say again why this is the only Lorentz invariant contraction? I didn't get that part.
So on-shell scattering amplitudes must be Lorentz invariant. And yes, all these spinor indices that are sitting around and vector indices, they will transform under Lorentz transformation unless they get Lorentz invariantly contracted into something else. So therefore, I know that the building blocks for an on-shell amplitude must be something that is made out of these things. And so I have to have something that's fully Lorentz contracted. Does that make sense?
Yeah, thanks. Yeah. Mm-hmm.
So whereas for scalar amplitudes, the Mandelstamms were my only building blocks, now my building blocks, well, they're still Mandelstamms, but they get translated into angles and squares, and the external wave functions will be translated into angles and squares. So everything, it turns out, can be written in terms of angle and square brackets. Very good. So that was fermions, and we saw also how that, an example with that. Now let me mention vectors. So vectors come with polarization, some with negative polarizations and with positive polarizations. So the way you write this, and here I'll just state the result, the way you write the polarization vectors in spinor helicity formalism is this funny way here. So what is this funny angle square spinor that appears there? That is really the contraction. If I write it in contracted in with momentum, you can see exactly what it is. It is just the matrix multiplication with a column and a row vector to create a 1-by-1 quantity, so to speak. Now, then there's a denominator factor. And one of the features that you see here is that the momentum P that appears, it appears in 2 places. That is going to be the momentum that's associated with the particle. But there's also another label in here. There's a label Q. And the Q that appears here is a so-called reference spinor. What does it do? It really encodes the gauge invariance, the gauge choice that you make when you're writing down an explicit polarization vector. That redundancy comes from the statement that I can take my polarization and shift by any number times the momentum of the particle, and I should still get the same answer. That is something that is sometimes encoded in ward identities or gauge invariant ward identities and amplitudes that you learn about in QFT. But that freedom in choosing Q is exactly equivalent to that shift by a number times the momentum. Okay. But these angles and square spinors, what do we do with them? Now there seems to be some funny new structures that I haven't accounted for before. If I multiply in a momentum as I did here, I can then see that if my momentum is on shell, p squared equal to 0, then I can convert my 2 by 2 vector into the angle square form. I can contract the indices, and you see that this is then nothing but the result that an angle square bracket is the same as a product of an angle bracket and a square bracket, so long as the momentum p is a null vector. I could also end up with a situation where these two types of brackets are multiplied together and contracted with the Lorentz index. Sigma here is contracted. Sorry, the Lorentz index mu is contracted. And in that case, there's a field identity that tells you that this is also just a product of angle and square brackets. Now, I'm not anticipating that all these things are getting memorized immediately. I show them to you to be able to make the following conclusion. Namely, that amplitudes of massless particles can be expressed completely in terms of angle and square brackets. So everything that we could have, polarization contractions, external wave function, everything translates in to just having two sets of variables, the angle brackets and the square brackets. That's it. But so what? Okay, why is this even useful? Well, it turns out that this is very convenient and very powerful, as you'll soon see. Now we're still on the plane for a little bit longer, but there's just one more thing we need before we're at the lovely beach on our vacation. That thing is actually pretty cool. It's called the little group scaling. Before I mention it, are there any other questions so far? I know this is sort of a speed introduction. We were on a jet plane.
Yeah, this Q can be arbitrary in epsilon formula.
Very good. Yes. So in these epsilon formulas, the Q's that are sitting here are indeed arbitrary. Sorry, that was the wrong one. The Q's that sit here are arbitrary.
I mean the data of the polarization, is it encoded in Q?
So the case choice of the polarization is exactly encoded in Q, and Q can be anything except P, because then the bracket and the denominator would vanish.
Up to a summation of P, like Q can, like that's what you were saying, right?
So Q can be anything. And in fact, in the final expressions for an amplitude, Q will have to drop out. And it's a nice exercise to take the cubic vertex, for example, from Yang-Mills theory and verify that Q really will drop out. So Q is unphysical, and the fact that there's a PQ thing that appears in the denominator does not introduce any spurious poles, because eventually the dependence on Q must drop out from a physical expression.
I see. These epsilons are basically bases, and it's not an independent, like it's not an independent data that you are mentioning. I mean, a linear combination of these two epsilons will be a general polarization.
It's a completely general polarization. Eventually, all these Q's will drop out. The other part of it is that I haven't really told you, if you have a specific 4-vector momentum, how do I actually compute the P angle and the P square? Now, that's an exercise that you can do, and I'm happy to point you to the right direction for some guidance on it. I'll do that in the reference for today. But we also don't need it. What you actually need most often are the abstract expressions for the amplitudes. And then we can work with those. And when you eventually need to evaluate them for a cross-section, it's actually quite simple. But often you just need the angles and the squares as more abstract placeholders. Okay. Yes. Okay. All right. Good. So let's talk about little group scaling. So the little group you can think of is the class of transformations that act on the space, but leaves an on-shell momentum invariant. So if I have an on-shell momentum that is null, so let's put it as this form here. That's our null vector. It's clearly null. But I can rotate it in the X and Y plane at no cost. So there's an SO2 rotation, which I can think of as a U1. This U1 rescaling, I can think of in the spinor helicity language as the following. So I defined my 2x2 matrix P in terms of a product of an angle of n square, a spinor. But that leaves it freedom in the description, which is that I could multiply my angle with any number T, so long as I multiply the square with some inverse of that number, T to the -1. Then that leaves P invariant clearly. And so if this t is a phase, then that exactly encodes the u1. What we're being a little sneaky about is that we will often think of the momenta as not just being real momenta, but being complex momenta. And that allows the angle and the square brackets to be independent. And I can actually take this t to be a complex number, not just something that has norm 1. That's a little bit of a subtle point, but it's not so important for us. Just think of t as a complex number here, and I can pick it to be anything I want. I can rescale my angle and square brackets without changing the momentum. So this scaling here is called a little group scaling, and I'm allowed to do it individually for any one of the particles, or as many as I want if I want to do more, in an amplitude. But the internal states of the amplitude do not change because they just depend on momenta, and momenta are explicitly invariant. The internal lines are something that depends on momenta that's explicitly invariant. But the external states have wave functions like the fermions, angle, and square bracket that will change when I scale them. And in particular, I could go through this list and check for a given helicity, how does the external wave function of that particle change with little group scaling? And well, for a scalar, it doesn't change at all. You get t to the 0. For external positive helicity fermion, it will scale with t to the -1, and oppositely for the negative helicity 1. And then if you go through and you look for the polarization vectors that I just told you, you see that for the positive helicity polarization, there'll be a t to the -1 from the numerator and a t from the denominator. So all in all, that gives you t to the -2. And for the negative helicity guy, you get the opposite. So putting all these 5 data points together, you can quickly infer that the amplitudes scale homogeneously with t to the -h for any one of the particles that I perform little group scaling on. And that's so important that I boxed it, that for any one particle I scale into external particle, there's a little group scaling that depends just on the helicity of that particle. It is also true for the gravitinos and for the gravitons. Okay, now we're at the beach. You can ease out, we can get out of the plane, we can take our face masks off. We're good. Now we're going to use this. And this is where the free ends.
Before we go on?
Good.
Can I ask one question before we go on?
Yes.
Why do we not scale the internal particles but with the external particles? I think I missed that.
Very good. So the internal particles, for example, let's take a fermion propagator. That would be something like a p/p². But this just depends on momentum, and momentum is explicitly invariant on the little group scaling. So nothing changes, nothing happens to it. Or if we had a scalar propagator, 1 over, say, let's say this comes in with momentum p1 and 2, p1 plus p2 squared. This is angle 1, 2, square 1, 2, and nothing scales because everything comes in pairs of angles and squares. So we do scale them. We do scale all the external momenta, scale one of the external momenta, and whatever depends on it inside will also scale, but it will always cancel out net. So there's no net scaling from what comes on the inside. Only the external wave function scale, and that's what gives us this uniform transformation rule. Very good. Okay, so the first application we'll work on is a quite important result that relates to 3 particle amplitudes. So in the first lecture, I argued that there's nothing interesting going on at 3 points because there are no non-vanishing Mandelstam variables. So for example, S12 was P1 plus P2 squared, which by momentum conservation was P3 squared, which is on shell, so that's 0. And likewise for all the other ones. But what about in terms of angles and square brackets? Well, in angles and squares, S12 is angle 1, 2 times square 1, 2. So it's a product of things that has to vanish, but that means that only one of them has to vanish. So that means either angle 1, 2 is 0 or square 1, 2 is 0. So that leaves me the opportunity to actually have something that is non-vanishing. And that's true for any one of the combinations of the momenta 1, 2, and 3. But let's now suppose that say my angle 1, 2 is the one that's non-zero. Then let me compute angle 1, 2 times square 2, 3. That is an innocently looking little combination. But let's notice that this has an angle 2, square 2 together. So that's really a momentum. So I can write this as 1, momentum number 2 sandwiched between an angle and a square with the appropriate indices contracted. If I wanted to put those in, this would look like A dot, B, B. But P satisfies momentum conservation. So this is the same as plus 1 P1 plus P3 dotted in. And now the following happens. I know that I have my massless Weil equation. And it will say that angle 1 with P1 dotted in must be 0 because the angle spinors are null vectors of this things. And likewise, P3 on square 3 is 0. And this is by the massless Weil equation. So what this means is that this whole thing is necessarily 0. But going into this, I had assumed that angle 1, 2 was not 0. So the only way this can then possibly be true is then that square 2, 3 is 0. But because angle 1, 3 was not 0, it meant that angle 2, 1, 2 was 0. Sorry, square 2, 1, 2 was 0. So all in all, you can then combine all this to conclude that at 3-particle kinematics, we must have that either all the square brackets vanish, which is the same as saying that all the 2-component spinors are parallel to each other. Either this happens or the same thing happens for all the angles. So that's how 3-particle kinematics is very special. So what does this have to do with little group scaling and everything else? Well, it tells me that if I want to try to build a non-vanishing amplitude at 3 point, I can only build it of either angles or squares. I cannot combine them. So let's suppose that we look at a situation where all the angles vanish, but I have the squares and they're non-vanishing. So that means that we are in this situation there where all the angle spinors are parallel. Okay, so I have some 3-particle amplitude. It has 3 particles with momentum 1, 2, and 3 with some helicities that I'll denote as superscripts. What can this possibly be? Well, it must be some function of these square spinors that I assumed were non-vanishing. So let's say that it's a square 1, 2 to some power that I'll call x3. It's 2, 3 to some power that I'll call x1. And it's 1, 3 to some power that I'll call x2. So I'll just label the x by the whatever label was missing in the square bracket. And it turns out, and I won't justify this, this is the thing that you would do when h1 plus h2 plus h3 are greater than or equal to 0. If you had a situation where the sum of the labels were negative, then you would use the angle spinors instead. Okay, so what? Well, what are we going to do with this? Well, we're going to do little group scaling. And I'll start with momentum 1. I'll start with doing little group scaling on that. So from what we learned about little group scaling, then if I rescale 1, it has to go as t to the minus 2 h1. That's how the amplitude has to scale homogeneously. But then when I remember that little group scaling takes a square bracket to t to the minus 1 times that square bracket, then I can also see from the explicit expression that I wrote from my ansatz up here that there are 2 places that I encounter square 1. And so that means that would also get a scaling from this that goes as t to the minus x3 minus x2. Well, so there's only one way that this can possibly work, and that is that we can conclude that minus, well, let's see, plus 2h1 must equal x2 plus x3. All right, now I can do the same thing for P2. And if I do the little group on P2, I'll find that 2h2 must equal x1 plus x3. If I do the same thing for P3, I'll conclude that 2h3 is equal to x1 plus x2. And so now I have a complete solution, that the powers of the square brackets in my ansatz are uniquely fixed in terms of my helicities. And it's easy to revert these expressions that I have here to get us that x1 is equal to h2 plus h3 minus h1. x2 is h1 plus h3 minus h2. x3 is h1 plus h2 minus h3. So what this means is that the free particle amplitudes by little group scaling are uniquely fixed. There's only one possible thing they can be. And that's true for loops. It's true for tree level. There's just no other kinematic solution. It's just fixed by little group scaling. And that's extremely powerful. By the way, you might wonder, well, let me make this conclusion in writing. So the free particle amplitudes of massless particles, the whole kinematics is uniquely fixed by the helicities of the particles up to an overall constant. By the way, what about that constant? What is the mass dimension of that constant? Well, if we look at our expression here, you may notice that each one of these spinners have mass dimension 1. That's because a Mandelstam has mass dimension 2 and it's a product of an angle and a square. So they're mass dimension 1. I also know that my amplitude overall must have mass dimension 4 minus n, which for this case is 3, so that must have mass dimension 1. So what I know is that 1 must equal the mass dimension of G plus the mass dimension of the brackets, which is x1 plus x2 plus x3, because I get 1 for every one of the square brackets. And that translates, if you add up what the x's are, this translates into the sum of helicities. So in other words, the mass dimension of G is 1 minus h1 minus h2 minus h3. Why does this make sense? Well, it makes sense that the higher helicities you have, the more negative mass dimension you have, because the higher helicities you have, the higher powers of x appear. That means that it's an interaction with more derivatives. And if you have more derivatives, you need to keep your overall dimension in your Lagrangian fixed. So that the action is dimensionless, and that gives you that G has to have more negative mass dimension. All right, questions, comments, thoughts? Does this remind anybody of anything? Yes, go ahead.
Does this imply that for some fixed helicities, up until some mass dimension, it always vanishes? There's one unique operator that won't vanish at 3 particles? So
it means that there is at most one possible operator for any kind of helicity arrangements. Yeah. At 3 particles. At more particles that can, with more fields or more particles, there can be more.
Yeah, of course. This only constrains the full 3 particle amplitude, not necessarily like the 3-point wave function that not wave function, the 3-point Feynman rule that could go to higher point
Right.
amplitudes, right?
So very good. So the Feynman rule for 3-point can depend on how I write my Lagrangian, but the on-shell amplitude that I would get out of it cannot possibly change. It has to be this expression once you convert it to 40 spin-helicity. It's pretty cool. You could ask what happens if I had picked angles instead of squares for some cases where I should have made the wrong choice. Is there a binary choice there? It turns out if you insist on locality, there's only one choice. And if people want to ask about that afterwards, I can go through an example if you'd like to see it. Cool. All right. So does this result remind anybody of anything they've seen before?
Like the conformal 3-point function, is that what you?
Excellent. Yes, that's exactly right. So that's what
I have a question related to that.
Good. Yes.
So like this you fix by little group scaling, which is like the scaling transformation there. Is there any analog of special conformal transformation in this case? Because
yeah, so the little group scaling sort of plays the role of the dilation in CFT. So the basic scaling transformation is essentially what goes in here. But it's just a little stronger here than it is in conformal field theory, whereas you need the special conformal transformations too. So let me actually elaborate a little bit on your comment. So this may remind you, as it did for some of you, of CFTs. And if you've studied CFTs, then you know that the 3-point correlator is fixed up to an overall constant. So 3-point correlators are fixed by conformal symmetry up to an overall constant. And in particular, if I pick scalar operators, the result I'm referring to is that if I have a correlation function of scalar operators at some points of exertion, y1, 2, and 3, then this takes the form of some constant that is not determined by the symmetries here, times, oh, maybe I should put this, I'll put this in a second line. Give me more room. Okay. So this is the difference between point 1 and 2 to the power of delta 1, the scaling dimensions of these operators, and you can see that this is exactly parallel to the case that we saw, but now with the helicities playing the role of the scaling dimensions, and the difference between points of insertion being the angle brackets or square brackets. Okay, so that's kind of nice stuff that you see this type of parallel, and it really is a logical parallel to that. All right, more questions. Okay, so let me pull our results over so that we have them, and we can now apply this to see different examples of results. Okay. Well, a simple example would be, what if I have a scalar? So let me make this example 1. If I have all scalars, h1, h2, h3 equal to 0, I get no momentum dependence, but my a3 will simply just be a constant. And that was exactly what we knew already, that there's only one choice when you have scalars. So just to make context with what we did last time. Let's take a look at a situation with fermions. So say particle 1 is a positive velocity fermion, particle 2 is a positive velocity fermion, particle 3 is a scalar. what can it possibly be? Well, you can see that in X1 and in X1 and X2, the polarization, the H's cancel, you get 0. And what you're left with is some constant times square 1, 2 to the first power. Okay, this is everything that it could possibly be. And it actually is the thing that fed into our little 4 fermion diagram that we did before. Notice here that this should have mass dimension 1. This has mass dimension 1. So that means that the coupling is dimensionless. And that's nice because we already knew that this was a Yukawa coupling. The other thing I wanted to point out here is that if I exchange particles 1 and 2, then I pick up a minus on the left-hand side. Oh, sorry, I'm on the right-hand side. This is exactly what I should, because exchanging 1 and 2 is exchanging identical fermions. And so this automatically encodes the Dirac stats that you should have. Okay. All right, so example number 3. Let's take spin 1 now. So I have particle 1 with spin with helicity 1, and particle 2 with helicity 1, and particle 3 with a negative helicity. You plug in to our result up here, compute the x's, and you find that the answer is square 1, 2 to the third power divided by 2, 3 times square bracket 3, 1. Again, the kinematics on the right-hand side ends up having mass dimension 1. And so you conclude that G is dimensionless. And that's what it should be if you're computing something like Yang-Mills theory in 4 dimensions. All right, what else should we look at here? Well, we have 2 identical particles. What happens if we exchange them? You should have both symmetry here, right? So what happens on the right-hand side? Disaster. You get a minus sign. The left-hand side is antisymmetric. I meant right-hand side. Sorry, maybe I'm left-right confused today. The right-hand side is antisymmetric under the exchange of 2 identical bosons. That seems like a big problem. So maybe this is just all nonsense and we should throw it away. Well, you know that Yang-Mills theory is not all nonsense, but there's another feature that we have left out. There's only one way to fix this, and that is to give these particles a label, an additional label. So if indeed these particles are photons, then there cannot be a 3-particle interaction. So the implication of this antisymmetry is that if they were photons and really had to satisfy pole symmetry, there is no 3-point interaction. But if these are gluons, then they must come with an additional label. And that additional label is something that is antisymmetric in the couplings. And so that is something with, for each of the 3 particles, is an antisymmetric structure constant. And that is exactly what should be there. So what I have written here is actually a color stripped amplitude. And the real amplitude with gluons is in fact the color ordered amplitude for gluons with that additional factor thrown in FABC or F123. And now indeed it has the correct Bose symmetry because you get a minus both from this part and you get a minus from that part. So we learned something very important, which is that you can only have 3-particle interactions with spin 1 particles if you have a non-abelian structure. And that's pretty cool. Of course, you knew this from Lagrangians and so on, but you see it here from a completely simple bottom-up approach, a very naive approach. Okay. I did a special case here where I picked 2 labels to be positive velocity and 1 to be negative velocity. We could do another example, which would be number 4, where I pick all my momenta to be say +1 velocity. And in that case, our formula gives us a unique choice. It's square 1, 2 times square 2, 3 times square 3, 1. And now we see that we have mass dimension 3 here, but the whole thing should have mass dimension 1. So that requires G to have negative mass dimension 2. And that's exactly what you would have if this came from an interaction that was F cubed. Again, you see that this must be a color ordered amplitude because otherwise it would be antisymmetric in identical labels. And that's why F3 is 0. Well, that's because F3 is actually 0 for abelian. So you actually need the non-abelian interaction also in this case. Makes sense? All right, I'm going to do one more example. What if I pick gravitons? So gravitons, +2 velocities for the first 2 and -2 velocity for the last one. You'll find that you get an expression solving for the x's that is again very simple. Dimensional analysis will tell you that the kappa coupling, I wrote now G is kappa, has mass dimension -1, and that's exactly what you have in general relativity. So again, that makes sense. A fun little feature is to compare this expression to what we had up here for the gluons. And we see that the graviton amplitude is exactly the square of the gluon amplitude. So indeed, this is actually equal to A3, 1, 2, 3 squared times the kappa factor. That's pretty cool. And that is a little bit of a pre-sign of the double copy that we'll learn about in the last lecture. Okay, questions, comments, thoughts? Okay, well, let's go back to something that we learned about last time.
I have a question.
Yes, go ahead.
How did we get these are gravitons? I mean, why not spin 2 mesons or something?
So spin 2 mesons. So spin 2 mesons. I mean, real spin 2 mesons would have to have mass. So
Right.
here I'm assuming that they are massless. So they are massless spin 2. But you could say, why should this actually be gravity? And I haven't proven to you that it's gravity other than the fact that its coupling has the right mass dimension to be gravity. But it turns out to be true that if I do look at Einstein gravity and I expand this around flat space, well, then I'll find some propagated terms and I have to do gauge fixing and I have to do all sorts of things. And then there's a 2 derivative interaction with free gravitons. And that's actually worse. They're endpoint interactions with 2 derivatives and everything for any n. But if I take this and I compute the matrix element of it, I would find exactly that result that we had above. If I convert to spin helicity formalism. It's not obvious from what I've told you, but it is true. The other thing that you do see is that, well, so this will come with a coupling kappa, which has to have that same mass dimension -1 as we just talked about. So it is actually true that it comes from GR, but it's not obvious, I guess, from what I told you exactly that that's the case.
Okay. Thank you.
But that leads us to another important aspect.
Can I ask a question? Too?
Yes.
For the M3 amplitude, if you exchange 1 and 2, does it tell you anything about the if there's a Abelian structure, non-Abelian structure?
Oh, great. So if I exchange 1 and 2 here, it should have both symmetry. And we knew that that was messed up for the color ordered amplitude, that it picked up a minus sign, but I have it squared, so that minus signs get squared. And it actually has the right both symmetry on the right-hand side in exchange of identical particles. So at this point, it shows that we don't need a color structure, but you can actually prove that you are not allowed even to have a color structure, that there can only be one graviton. That's another amplitude result that you can pull out from here. But it's not from what I have just shown you a 3-point.
Thank you.
Cool. All right. Good. So in lecture 1, we talked about how 3 amplitudes have factorization channels exactly in the places where they exchange physical particles, and the amplitudes factorize into lower point amplitudes. So we have now 2 facts. The 3 particle amplitudes are uniquely fixed up to an overall constant. And we also know from lecture 1 that n particle amplitudes factor into lower point amplitudes on their poles. And these poles are all simple poles. So you can put these 2 statements together and realize that you have a very good shot at 3 amplitudes determining all 3-level amplitudes. So you could ask, question mark, if this implies that 3 particle amplitudes determine all endpoint 3 amplitudes. And here I should have added 3. That is true, at least in some cases. So a case where this is true, it's true for Yang-Mills theory, also for super Yang-Mills. And it is true for gravitational amplitudes too. So the way you can prove this goes beyond what I'll show you in lecture, but it is true by use of what is known as BCFW recursion relations. And I'll give you a reference to those and how recursion relations in general work for amplitudes in the modern versions. I'll give references to that on the wiki page so you can see. So if you think about this, that might seem a little surprising, because what you learn about Yang-Mills theory is that Yang-Mills comes from something like trace f squared or trace f mu. And when I write this out schematically, I'll get something that is dA, that gives me the propagator, plus something with 1 derivatives and 2 a's, plus something with 4 a's. Okay, because f mu nu is dA nu d nu a mu plus the commutator. And when you expand out the product in the non-abelian theory, you get these interaction terms. So what we have seen is that the 3 particle amplitude is uniquely fixed, and that would correspond, and you would get exactly the same result by using the Feynman rules I gave you in spinor helicity language and computing the 1 derivative 3 particle interaction that you get from expanding out f squared. So this is actually completely compatible with what we just determined from little group scaling was the only thing it could be. So this gives the plus plus minus amplitude, and give minus minus plus plus. It can't give the other helicities because they came from an f cubed. We don't have that here. What is surprising is the statement that I can just take the free particle input, this part, and determine all tree-level amplitudes. Because after all, when I use Feynman rules, it seems to be important that there's also an f to the 4 term. So in a sense, it's very surprising, perhaps, that you can determine everything from free particle amplitudes, all endpoint tree-level amplitudes from just the free particle information when the Lagrangian has this 4-particle interaction. But the reason a to the 4 is there, it's simply to ensure the gauge invariance of an action in this form when it's written in this manifestly local form with some set of redundant variables. So A4 is there to ensure off-shell gauge invariance. But it's actually not there for any kind of on-shell reason. And we can tell that it's not needed on shell because we have recursion relations that construct all the endpoint amplitudes.
Question?
Yes.
Is this the same as saying that the A4 coupling is not independent of the A3 coupling?
That's correct. Yes, exactly. So once I know the free particle coupling, so you may know this exercise, I think it's in Peskin and Schroeder, where you compute the pole diagrams for the 4 gluon amplitude, pretending that you don't know a to the 4 is there. And then you check the rule that when you replace a polarization vector with the momentum of that particle, you should get 0, that gauge invariant one identity. And that fails unless you have that a to the 4. But what it checks is the off-shell gauge invariance. But when we only stick to on-shell amplitudes, we don't have to worry about the a to the 4.
Okay, thank you.
Very good. So you can reconstruct the Lagrangian from the amplitudes if needed, but all the physics information sits already at 3 point, which is kind of remarkable.
It should also not fail at the loop level, right?
So at that's right. So at the loop level, ask me afterwards about the loop level, because I can say more there, but I also don't want to go away from the main line of thought here. So ask me afterwards. So for example, we can determine a Yang-Mills amplitude from these recursion relations and a few pages to derive. So here's the formula. I have a whole bunch of positive helicities, and then I'll pick to just have 2 negative helicities at positions I and j. And the answer for this entire amplitude is I, j angle to the 4th divided by 1, 2 angle times 2, 3 angle times 3, 4 angle, dot, 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 and 1 angle. So this is basically a cyclic contraction, a cyclic expression, and that reflects that here there's a trace that's pulled out of all the generators, so the expression has to be cyclic. And this is color ordered, which means that it really should be multiplied by a trace T1 to Tn, and these are the generators. Okay, so there's such a cyclic product here that reflects the cyclicity of the trace, but then there's just the thing that distinguishes the negative helicity particles I and j. So this expression is known as the Park-Taylor formula. And it's been known for years, but it's extremely easy to prove using recursion relations. And it's also known as the MHV amplitude, where MHV stands for maximally helicity violating. Now, if I were to compute this expression from Feynman diagrams, at, for example, n equals 7, I would need 154 diagrams. So it is one example of using spinor helicity. It's an extreme simplification of the answer, but where also the techniques that have been developed in the language of spinor helicity allows you to derive such formulas for all n that would seem intractable even with standard Feynman rules. Of course, people developed tricks in the past to do this, but this is a very neat way of doing it. Since we talked about gravity, then we had the statement up here that the expansion of the action for gravity. Oops, I should probably put that back in. Oh no. Here we go. Sorry. So we had this expression here for the expansion of the Einstein-Hilbert action. There it is. And the point I wanted to say here is that this has endpoint pseudoderivative interactions for any n. If you try to compute something as simple as a 4-particle diagram like this in the standard de Donder gauge that people use to fix the gauge in gravity as a standard measure, then you find that this is about 1 page of LaTeX. So that's pretty awful. And you can imagine how calculating n-particle tree-level diagrams in gravity is an absolutely horrible exercise where the endpoint interactions blow up significantly because there are so many different ways of contracting the indices of the h's that each have 2 indices. You can just imagine the mess that this creates. Nonetheless, just like before, thanks to recursion relations, the free particle information here fixes everything for you. So that means that that little innocent free particle interaction that we fixed by little group scaling actually determines all of classical GR, at least in a certain sense. So what do I mean by this? I mean that tree level is basically equivalent to the classical theory. And so our nice little 3-point graviton amplitude should in principle be enough to know everything that can be solved by equations of motion, at least perturbatively around flat space. So people often say that you can then use this to perturbatively construct as an expansion around flat space, the Schwarzschild solution from knowing the free particle scattering that you fixed by little group scaling. Of course, those are fancy words, and to actually do it requires way more work. But the principle remains true that this little term here determines everything that we need to know to calculate all tree level, all scattering, classical scattering in gravity, and all the rest, all this stuff that sits out here, that was just needed so that we can write an off-shell Lagrangian. But it's actually, strictly speaking, not needed on shell.
Question. Would this also work for doing perturbation theory around a curved background?
So that's much trickier because then you have to figure out what your observers are and your asymptotic states, and what you talk about might be observer dependent. So this is much trickier, as you know.
I mean, just something as simple as, say, black hole graviton scattering.
So if I can treat, I think you might be able to do some probe calculations like this, where you treat the black holes and effective potential.
Yeah.
And one place where this has been used extensively, and this is a little bit on the side, is to do scattering where I have some massive, let's pretend that the black hole is a scalar with some mass m, and now it interacts with another scalar. It could have some other mass, but we also pretend that that is a scalar. And now they interact gravitationally. And if I just calculate this diagram, that should basically model the Newtonian potential. So this gives me Newton. But then I can do more, right? Then I can exchange diagrams like this. I can have self-energy diagrams, all sorts of things. So this gives me quantum corrections to that. And long ago, Donahue and collaborators starting writing down from amplitudes ways of extracting the effective potentials, figuring out what the classical corrections are in higher powers of G in G Newton, but also in higher powers of H bar, basically. So quantum corrections as well as nonlinear corrections in gravity. And that can be done. And more recently, this has been used extensively to calculate effective potentials, like the effective Hamiltonian of binary in spirals from amplitudes. So that's a new way of extracting this, and they can get to something like third post-Minkowskian order. They're trying to push the barrier on that. So that is a nice connection to things like LIGO physics and so on. And of course, in these interactions, gravitons radiated off would be your gravitational radiation there. Cool.
Henriette,
yes.
you have 5 minutes left.
Great. I will finish in 5 minutes. I want to go beyond 3 points now. And just give you one example. So suppose I wanted to say I have some endpoint local operator in my Lagrangian that I'd like to understand. For example, that could be, you know, trace f to the 4 or an abelian f to the 4 or something like that. So how would I go about doing this? What would be the endpoint amplitude that I would get out of it? This would have to be some local, meaning no poles. So the matrix element of that is some local polynomial in the angles and square brackets. And it has to be of a certain degree, which for f to the 4 will be, this has 4 derivatives and 4 a's. So that would be something of 4 derivatives, so of kth order, where k counts the number of derivatives that would be in there, to, well, essentially k derivatives. And the angles and squares that you construct this of must be subject to 2 things, namely momentum conservation, which says that the sum of all the momenta has to be 0, and something called the Schouten identity. What is the Schouten identity? It's the statement that all these 2 component spinors, well, they lie in a 2-dimensional space because they're 2 component. So if I write a linear combination of 3 of them, they must be linearly dependent. So any 3 2-component vectors must be linearly dependent. And that comes down to saying that ij angle with a k spinor plus the cyclic rotation of those labels this must vanish. And a similar identity for the squares. Okay, so before we had momentum conservation for the scalar particles for the Mandelstams, now we have it for the angle squares in this language here. Okay, so let me just try to do an example with this. If I have an abelian f to the 4 operator, it has 4 derivatives and 4 of the scalar of the vector potentials. And what could I possibly do? So an amplitude like this with positive velocities of 2, I have 2 positive velocities and 2 negative velocities. There's only one possible thing this can possibly be of the right mass dimension, and that's angle 1, 2 squared times angle 3, 4 squared. And you can see that this must have a coupling of mass dimension 1 over lambda to the 4, where lambda has mass dimension 1. Otherwise, the dimensions don't work out. And then if I tried the same thing with all plus velocities, that would give me, again, something with the same mass suppression. And now I just have to add the permutations to make this manifestly Bose symmetric. There's only one choice there. And if I look at the last independent option with 3 pluses and 1 minus, I see that there's no way I can possibly Lorentz invariant contract all the indices. So this has to vanish. So at the Lagrangian level, this is related to the fact that there are two possible operators that can sit in the Lagrangian. One is f mu nu contracted this way squared. And the other one is the cyclic contraction of indices. And it turns out that the positive helicity arrangement is exactly the first one of these minus 4 times the second one of these. So in a sense, the helicity basis gives you a particular basis of your operators. Now, it would happen to be that this exact combination is actually what appears if you look at the expansion of the action that is minus the determinant of eta mu nu plus 2 pi alpha prime f mu nu. So that gives you a standard f squared plus exactly the operator that I wrote up here. That's not a coincidence, because it turns out that this action is the Born-Infeld action, the low energy effective action on a space filling brane. And it has the property in 4D that any amplitude it produces must have the number of positive and negative helicity states to be the same. In other words, it vanishes unless n plus equals n minus. And this is the amplitude manifestation of the fact that this action has electromagnetic duality. It's not enough to fix this amplitude uniquely, but it's related to the fact that it has electromagnetic duality, that this is precisely the operator that comes out. And in any case, this is extremely powerful. So these ideas are using spinor helicity to construct a basis of local operators is extremely powerful. And last time I mentioned that such techniques are used in standard model effective field theory, and they can be used in determining operators in UV supergravity, and well as many, many other applications. And if people want to know more about that, I'm happy to talk here afterwards or more over on Gather. So I'll end here for today, and then next time we'll talk about divergent soft theorems for particles of a variety of spin.
Thanks, Henriette. Okay, are there any quick questions now?
Can I still ask the question I asked earlier about the fact that A4 doesn't have independent coupling should also be true at loop level. So then even at loop level, 3-point amplitude should determine the higher point amplitude. Is that still?
Yeah, that's right. So there's a couple of things to say. So in principle, that's right. One way to think about it is if I do loops, then I can perform unitarity cuts and get from loops to trees. And so long as I can do that, then my loops are determined by the trees. And that way, what you said was true. The sort of small thing that enters here is that not everything in all loop amplitudes is determined only by the 4-dimensional cuts, but you may also need d-dimensional cuts, or in other words, there can be rational terms. So you basically have the cut constructible part plus rational terms. And you can do the rational terms by d-dimensional cuts. And I think in that spirit, it remains true that the 4-point doesn't have a physical effect there. But it's a little more, I think that the statement is a little more subtle. The other thing, somebody asked about loops last time in connection to soft limits. And that has actually been a cause of some confusion early on in the field, because the fact is when you have only massless particles, then your loop amplitudes tend to be IR divergent. And so you need to define what the physical part of the amplitude is, that the part that actually makes sense after subtracting off the after contracting off the IR divergences. And so when you couple the IR divergences in the loop calculation of the amplitude with a soft limit that can also create a divergent part, it becomes kind of confusing because you're doing a double soft You're taking sort of a double limit in some sense. I have dimensional regularization epsilon and I have a soft epsilon, so to speak. So it's a little more subtle than that.
Okay, thanks.
Can I ask a question?
Yes.
Previously you had this plus plus just one page before this plus plus minus minus giving you the action of Born-Enfield. Now there are two answers, right? So
Oh yeah. So
one
good.
of
So
them
maybe I
gives
should
rise
be
to
more
this
precise. So
action.
what I good, go ahead, maybe ask your question.
Yeah, so I'm saying this Lagrangian, this combination, trace f square square minus 4f to the power 4 comes from this plus plus minus minus. Now, what Lagrangian gives rise to the second answer, that plus 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 plus?
Right, great.
Is it the
So
same Lagrangian?
if I just took say this operator, it would contribute to both these two amplitudes with certain coefficients. And likewise for the other operator. So there's some other linear combination of these two that produces only the all plus, and I forget what it is. But you could work that out. But it happens to be that the thing that this square root produces is precisely the thing that only produces plus plus minus minus. That was what I wanted to get to.
I see.
Yeah, the other part you can think of is that the helicity basis is not like, it's not that one of them corresponds to just one of these two Lagrangian operators. It's some linear combination. So that means when you work on a helicity basis to count and characterize the local operators, it might not be the simplest way of writing them in the Lagrangian. So they might end up being some
Yes.
linear combination.
One of them leads to this Born-Enfield action.
Yeah.
I was asking what the other one leads to. Like, is there any physical significance to that one?
A generic theory of nonlinear electrodynamics. So nonlinear theory of this form here. Well, this operator, whatever it is, will have both components, both the MHV and the all plus, and for CPT, and there is also the all minus. It will have both generically. So if, for example, if I look at low energy QED, so I have QED, and I integrate out the electrons and positrons, then I end up in the low energy IR with just free Maxwell. But the effect of integrating out the massive electron positrons is that a little bit away up the energy level of this RG flow is nonlinear electrodynamics with a coefficient of some A, which is determined by the mass of the electron, essentially, and some factors of pi and so on. And this operator here is not the same as the Born-Enfield operator. This contributes both to the all plus and to the plus plus minus minus. So for example, this action that comes out in this way is called Euler-Heisenberg. So that is just one example of one that has both classes of amplitudes for photons in it. But I don't know if there's a significance to a thing that only has the all plus, if that's what you're asking. Yo, actually, there is, sorry, I should say that there is. So the only all plus is something that is called self-dual Yang-Mills, I guess. Self-dual, is that the self-dual theory, or if it's not abelian, it would be called self-dual Yang-Mills. And that's kind of a nice theory to work into. That's what certain other reasons.
I had a question.
Go ahead.
Yeah, so it seems like, I mean, these amplitudes, you know, this plus plus, all plus and plus plus minus minus, these amplitudes are fixed by duality, which relates to the equations of motions, right? So that's a symmetry of the equations of motion, not necessarily of the Lagrangian.
Yes.
But it seems like you are saying that this duality also, in a way, fixes the Lagrangian. So is that a
good.
contradiction?
No. So the statement is that 4D Born-Infeld has electromagnetic duality, which is at the level of the equations of motion, not at the Lagrangian, as you said. This does not mean that electromagnetic duality implies Born-Infeld. That is not true. If you want theories that have electromagnetic duality, there's a whole one function parameter worth of such theories whose equations of motion have electromagnetic duality symmetry. And Born-Infeld happens to be one of them. But it's not unique as a theory that has electromagnetic duality. So its action is not fixed by this. So,
Okay.
from an amplitudes point of view, you'd have to go to 8 point to see that there are operators that can come in with arbitrary coefficients and satisfy this type of electromagnetic duality identity here, which is all you need from the amplitudes point of view.
Okay, let's stop there. And if you want to hang out and ask Henriette, then you're welcome to, and maybe you can, shepherd people across together if you're happy with that.